All right, so we went over a concerted substitution reaction mechanism and a concerted elimination reaction mechanism, and it would be great if we were done there, but unfortunately we got two more react mechanisms to go over. This is the SN1 and E1 reaction mechanisms. They're obviously going to be very useful, but one key difference being instead of being SN2 and E2, it's SN2 or SN1 and E1. So what does that mean? Well, so first let's just look at an example of a reaction that does occur, but clearly doesn't follow either of those two mechanisms, SN2 or E2, right? So let's take this tertiary alkyl halide. Well, we know that's not going to go SN2. SN2 is out of the question because you have a sterically hindered alkyl halide, right? Tertiary alkyl halides will not undergo SN2. And then we're going to mix this with ethanol. Well, ethanol is not a strong base, right? So we know it's not going to undergo an E2 mechanism. It's just not a strong base, which is what we need for those E2 eliminations. Yet nonetheless, we wind up with substitution product and elimination product. So clearly there's something else going on here. This is going to be our stepwise mechanisms, okay? So let's just see what we mean here. Stepwise meaning that there's more than one step involved. Most importantly though, is that the kinetics are unimolecular, meaning that the rate is proportional to only the concentration of the alkyl halide. The concentration of the nucleophile or the base doesn't affect the reaction rate at all. And that's because the first step is actually the loss of a leaving group, right? SN2, E2, you had either proton transfer or nucleophilic attack happening at the same time. Here, they don't happen at the same time. The first thing that happens is just the loss of a leaving group, and thus the formation of a carbocation intermediate. That carbocation then goes on to react either as a substitution or an elimination. But both of these reaction mechanisms have that same first step, and that is the formation of the carbocation. And again, only the alkyl halide is involved in that step. The nucleophile isn't involved at all. So that's where the ones come from. So this was, I sort of primed it before, but nonetheless, just to reiterate, it's a really common point of confusion to mix up the fact that an SN2 reaction happens in one step. An SN1 reaction happens in two steps. First step being the formation of the carbocation, the next step being the nucleophilic attack. So remember, the 1 and the 2, they don't correspond to how many steps there are. It's how many species are involved in that rate limiting step. And again, for SN1 and E1, it's just the alkyl halide, and it's the loss of that leaving group. This is my really messy proportional 2 sign. All right, so then let's do a reaction mechanism here. We have this tertiary substrate, so it's going to proceed through this stepwise mechanism where the first thing that's going to happen is the loss of a leaving group in order to form that carbocation. And then after that occurs, in a second step, we have our nucleophile attacking, and that's how we get our substitution product, right? So this is SN1. Substitution reaction happens. Unimolecular, meaning that rate limiting step only involves the alkyl halide. One thing that's really, really common to see for SN1 reactions are what are called solvolysis reactions, which means that the real key player is going to be the solvent. Okay, so let's take a tertiary alkyl halide dissolved in an alcohol solvent such as ethanol. Well, the first step is, again, it's going to be this SN1 unimolecular, where I'm going to lose a leaving group. I'm going to form my carbocation. The next step is my solvent, my ethanol, is going to do the nucleophilic attack. That leaves this protonated intermediate here. So there's actually a third step in this reaction, which is, I'm sorry, let's do this more clearly. Third step in this reaction, which is this, the solvent again, that ethanol is going to come and retrieve that extra proton. So this would be a last step, which is a proton transfer. And that would form our final substitution product. Okay, so very common, you know, it would be the same thing if you dissolved it in methanol or even water, but you would have the actual solvent playing the role of the nucleophile in one step, and then a base in the second step, or I guess the third step, but yes, the last step. And if we wanted to look at what this would have, you know, this would look like in terms of our free energy diagrams, remember those SN2 reactions were kind of your simple one-step boom, right? Here we have these intermediates that are being formed. So the first thing that happens is we have a loss of a leaving group. So that's this coming off there. That forms this higher energy carbocation intermediate. That carbocation is what's attacked. Actually, let me use a different color. By the ethanol, forming yet another intermediate, which has this protonated oxygen. And then lastly, we have this proton transfer step to get us to our substitution product. But what is the rate limiting step in this reaction? Right, remember what portion of these diagrams correspond to rate? The rate limiting step, or the slowest step, is going to be the one with the highest activation energy. And so it's the formation of that carbocation. That initial first loss of leaving group step is the slowest step in this reaction mechanism. From there, everything happens kind of quick. So to pick it apart, right, the S, it's a substitution. It's a SN, a nucleophilic substitution, but it's unimolecular, meaning that the only thing that matters in terms of the reaction rate is the substrate, or more specifically, the alkyl halide. The rate of an SN1 substitution depends only on that concentration of alkyl halide. Again, just making sure that we can do our reaction mechanisms. What are we going to do first? If we know it's an SN1, we're going to get rid of that leaving group. That's going to leave us with a carbocation intermediate, so loss of leaving group, that's that first step. And then nucleophilic attack, that's our second step. That's an SN1 mechanism. Again, SN1, think carbocation intermediate. Really, when we're talking about the ones, the SN1, the E1s, you want to think carbocation intermediate. And an E1 is sort of no different, except you get the elimination product, but that first step is that loss of that leaving group, that carbocation intermediate. What's different is what happens next. Instead of your nucleophile attacking that electrophilic carbonyl carbon, it actually reaches over and grabs that hydrogen on the beta carbon. Then that comes down. But this is now a second step. So beta hydrogen elimination, I guess we have loss of leaving group first, beta hydrogen elimination, or what we would call proton transfer. occurs next, and that's how you get your elimination product. But notice that this is the same first step as it would, same first step as SN1, right? The difference is what happens to that carbocation intermediate. Now the ethanol is acting as a base because it's accepting a hydrogen as opposed to attacking that electrophile. Okay, but interestingly, these will follow the same kinetics because that rate limiting step is the same, right? Whether we're talking about the E1 or the SN1, the same first step is the formation of that carbocation intermediate. E1 is a little bit higher in energy than the E1 product is a little bit more higher in energy than the SN1 product. Why would that might be? Well, what do we know about entropy of double bonds? They can't rotate freely, so they don't have the same rotational entropy. Not only that, but a pi bond isn't as strong as a sigma bond. So generally speaking, we would expect the E1 product to be slightly less favorable from a thermodynamic standpoint than the SN1 product, than the substitution product. I guess really the main takeaway from this would be E1 is the rarest of all the reaction mechanisms. We'll compare and contrast here in this next, I guess 2 lectures from this, but yes. But nonetheless, that's the main takeaway from this, I think. And that they have the same rate determining step, right? That same intermediate, that's key. All right, so now one more complication we have to think about because we're talking about carbocations is the potential for these rearrangements that we saw last chapter. All right, so let's take a look at this example here. So let's say that this is going to undergo an SN1 reaction. Well, what's my first step? Loss of a leaving group. And so that would leave me with this compound here. Now, if we had our water attack as a nucleophile, attack this electrophile, we would expect to get this product here. This would be our normal old SN1 product. But what do we know about carbocations like this? They don't just stay like that. Instead, you would expect for, let's actually put it over here. You would expect for this hydrogen to undergo a hydride shift, leaving us with that more stable tertiary carbocation. And that's what would then be attacked by the water, right? So in fact, so another potential product would be the SN1 product after hydride shift. And what we're gonna see is that this is actually the only substitution product that we would have to worry about. SN1 of that secondary carbocation wouldn't occur, right? Those rearrangements are irreversible in favor of that more stable alkane. More stable carbocation. Likewise, same thing over here, right? So if we had that first step being our loss of a leaving group, we would have a carbocation that looks like this. If water did attack, that would give us our regular old SN1 product. After that, I'm sort of being lazy by not then showing the deprotonation step that would happen as well. But really, this doesn't occur because instead, you have a methyl shift producing that nice, stable tertiary carbocation. And that's what the water will attack. Okay, so again, our major substitution product here will be after the methyl shift. I don't know why they say methide, but it's a methyl shift, okay? I'll just give you the punchline as to why this is kind of a pain in the butt. I mean, it's probably kind of obvious because you got to look out for this. We're going to see that only tertiary alkyl halides undergo SN1 and SN2 reactions. So normally we wouldn't even look at a secondary alkyl halide, as is these two are both secondary alkyl halides, as undergoing SN1 or SN2. The exception is going to be these two scenarios right here where there's the potential for the hydride shift or methyl shift that form a nice stable carbocation. Then those would undergo SN1 and SN2 type reactions. So this is just kind of a special consideration that you're going to have to keep in the back of your mind that could happen when you have a lot of branching on your alkyl halide. Another example being here, you know, down here, normally we wouldn't think of a primary carbocation as getting to form at all, which is why here you have a methyl shift and loss of leaving group happening at the same time in order to form that more stable tertiary carbocation. That can then be attacked by the water. If you're going to complete your reaction mechanism, you're going to have another step where you have to deprotonate that water in order to get your alcohol group.